Hey guys, Mr. Patterson here with you looking at section 11B, row operations. This is for IB math analysis and approaches, the HL level, and we're going to be looking at 11B from the Haese book. In this section, our objective is to manipulate linear systems using row reductions to solve linear systems. So we already know that when we're looking at equations as a system, like we have here 2x plus y equals -1 and x minus 3y equals 17, that we know that it has the same solution as the same system with the equations in reverse. We also know that it has the same solution as any scalar multiple of any or both of these equations as well. So we're going to be using this idea to kind of manipulate the equations in order to make it easier to solve the system. So how do we do that? Well, if we were to be looking at this example, the same 2x plus y equals -1, x minus 3y equals 17, if I called the first equation equation 1, the second equation equation 2, if I did 2 times row 2 minus row 1, you would see that we would essentially be canceling out the x terms. This, back in algebra, was referred to as elimination or linear combination, and that would allow us to isolate one of the variables, and we end up finding that y equals -5, right? And then we could plug back into either equation to find the x that corresponds with it. So through that manipulation, though, we come to the conclusion that we can manipulate one or both rows in order to solve the systems in a little bit easier manner. And that's what we're going to be doing with row operations. But before we get too far into it, we need to make sure that we follow certain guidelines when we're dealing with these systems, or as we're going to see, we're going to put them into augmented matrices. And then we have to follow these rules to make sure that we're not changing the equations in a way that we would not have the same solution. So interchanging rows, that's fine. We can switch which one is first, which one is second. We can replace any row by a non-zero multiple of itself, meaning we can multiply a whole row by a scalar of itself. And we can replace any row by itself plus a multiple of another row, which we just saw in the previous example there. So as long as we're only doing one or two or three of these things, then we are fine going ahead and working through these row operations. So if we were to take the example that we just looked at and put it into an augmented matrix, augmented matrix is basically the same thing as saying, as long as you have it in an ax plus by equals c format, standard form of a line, then you could basically just get rid of the variables, put this vertical line here separating the variable terms and the constant terms, and then we can go ahead and do our manipulation. So here from this first augmented matrix to the second augmented matrix, all we're doing is we're switching x and y. Notice the notation here. R1 goes to R2, and since the arrow goes both ways, R2 goes to R1. Then we could do a little bit more manipulation with it by saying, once we have it in this format here, we could multiply row 1 by -3. That's why we see this -3 times R1, and that goes to R1. So notice the second row remains exactly the same. It is only row 1 that is getting multiplied by that -3. All right. Then if we wanted to do even one more row operation, we could leave the top row by itself, and we can make the bottom row 2 times R2 minus R1, and that is going to take the place of the current values that are in row 2. So if I say 2 times R2, that means I'm going to take 2 times this one value, and then I'm going to subtract the value that's in the first row. So 2 times 1 is 2, minus 2 is 0, excuse me, and that's why we have this 0 in this first location, second row. Same thing here. If I did 2 times this -3, that gives me -6, and -6 minus the 1 gives me the -7, and same thing to get the 35 here. Now, the reason that this particular row operation is very valuable to us is because now I can look at it and say, oh, this is 0x minus 7y equals 35, which is the same thing as saying negative 7y equals 35, and therefore we have it such that y is going to equal negative 5, and we can plug back in to find the x value as well. So that's it for this first section here, looking at row operations. We're going to continue in the next couple sections talking about how to work with these augmented matrices to make it easier to solve 2 by 2 and 3 by 3 systems. But for now, I'd like you to take some time to work on page 258, numbers 1 through 4, giving you some practice with these row operations. That's it. Have a good day, guys.